Good morning. What I'd like to share with you this morning is two different narratives, actually. One is a narrative which is a spectacular success in the medical field. And the other one, I would characterize it as a spectacular struggle. I wouldn't quite call it a failure, but it's a spectacular struggle because we do see light in the end of the tunnel for the second virus also. So let me start with some of the major milestones or millstones, if you will, on viral vaccine development. The spectacular success, there you go. The spectacular success I'm going to talk about is hepatitis B virus. And that vaccine has saved millions of lives. It has also halted the disease in many millions of people. So these lines where the arrow is completed are the ones where everybody knows about polio, measles, rubella. And the places where you don't have arrows completed are still, where we are still struggling to come up with a vaccine. And that includes herpes simplex virus, hepatitis, the HIV, HCV, etc. So let me start with the success story, hepatitis B. The virus is a circular DNA. Actually, it's called a flexible DNA because a portion of it is single-stranded, and it basically comprises the surface antigen and the core antigens, etc. The key antigen actually here is hepatitis B surface antigen. That is really the key molecule. That molecule can be found inside the virus, and it can also be found as particles that are oblong or circular by itself in those sizes. Now, what is interesting about the hepatitis B surface antigen molecule is that, on the one hand, it is obviously critical for the virus to enter the cell, but we still don't know the mechanism by which it manages to infect the host cells. On the other hand, it has been the single biggest reason why we achieved spectacular success in vaccines and immune therapy with respect to hepatitis B. So a brief overview of the pathology is basically hepatitis B causes sickness or hepatitis. The virus causes hepatitis simply because it's too good of an inflammatory reagent. It actually stimulates the immune system in a big way. So what happens is initially cytolytic T cells are stimulated and they kill off a portion of the virus, and then they go in and they secrete cytokines, which then creates another cytokine storm, cytokines like interferons and all that go and kill off more of these cells that are cytopathic to the virus. At the same time, they also recruit polymorphonuclear cells and lymphomononuclear cells, which are the cause of inflammation. So that is really the sum and substance of it. So the fact that the immune response is so terrifically efficient against hepatitis B is the cause of the liver disease, basically. And there is a lot of evidence, which I won't go into today, about why hepatitis B carriers are also highly risk-prone for hepatocellular cancer. Quick overview of the epidemiology. Basically, it's this heat map shows you the worldwide incidence and prevalences. Roughly 400 million people today are carriers of the disease, and they have to be contained somehow because there's no way it gets completely cleared. So what is the main? Most of the studies of HBV happened in Taiwan because there's a major focus there. Because the Chinese Asian populations are very prone, and so the Taiwanese government made a major effort, and fundamental work was carried out by R. Palmer Beasley when he was in Taiwan. And a lot of the work I'm going to talk to you about today on hepatitis B is about the work done by Beasley and his students Clad Stevens and so on. So 15% of adults are carriers of. This is the way you identify if you have hepatitis B, is through the surface antigen. Hepatitis B surface antigen. There's an immunoassay for that. Very fundamental piece of information is 40% of infants born to carrier mothers become carriers. And in the next slide, I'll show you something even more egregious about this. And it is highly correlated with the E antigen, the hepatitis B E antigen. So if a mother is hepatitis HBs AG positive and E positive, there's a very high likelihood that if they're pregnant, the infant will get it. And this was done, a longitudinal study was done in school children, college students throughout, and this is very clear that if you want to stop the spread of hepatitis B virus, you really have to go at the pregnancy stage itself. right there. And this is the data that I'm talking about. 90% of infection occurs within the first year in the infants, and then it progressively goes down. So it's very strongly age-related. So the goal of then stopping hepatitis B is really to find those mothers who are carriers, and if they become pregnant, to stop it, somehow treat them so that they do not pass it on to their child. And so, a major development that happened in hepatitis B was the development of an immune globulin therapy. And again, it was basically against hepatitis B surface antigen. It was fairly crude. Going back to 20 years, they pooled together the serum of people that had been infected with hepatitis B and simply, processed it and got the IgG out. So it's called HBIG. It's nothing spectacularly different. It's just a polyclonal antibody preparation. And this is what they did. They looked at infants of mothers who are AG and E positive. And this trial, so this is a placebo. You can see that, a huge amount of the children that are born get infected. If you give HBIG in one dose, you get a reduction of almost 50%. And if you take it to 3 doses, chronic HBV goes down to 26%. There is still a gap. There's still a gap, but you've reduced your problem significantly with administering HBIG before birth to the mothers. The second aspect of this is the development of a vaccine, again using hepatitis B surface antigen. So surface antigen is so immunogenic. Initially, the preparation was made out of simply purifying these 42 nanometer particles by ultracentrifugation. Subsequently, recombinant DNA methods were employed, and a vaccine was made using basically expression in yeast by Chiron. Well, Chiron actually sold that technology to Merck, but so Bill Rudder's group did that. And so when that happened, again, they found this. I'm not showing the data here, but essentially there's a gap. So the thought occurred naturally, how about if you combine the vaccine? The reason is, the reason why there's a gap here is because if you, the immunoglobulin disappears from the system. So the HBIG serves as a bridge to the infants in the beginning because they don't have their own immune system. So you give the HBIG. The thought is, by the time they develop their immune system, and if you give a vaccine, that's going to kick in. Now that's going to be permanently protected for life. So that is the strategy, right? So let's see how it works. So what they did was, this is a very busy slide, but the bottom line is it worked. So you gave 0.5 ml of HBIG, and then you treat it. This is the schedule. I'm only going to talk about the bottom portion because nobody uses the plasma-derived vaccine anymore. It's all recombinant. And they settled on 5 microgram as a dose. In fact, that, to make a long story short, there's 91% protection with the combination. Now, you could ask, why didn't it go to 100%? And the reason for that is there's about 5 to 7% of people that simply do not respond to surface antigen. They have a particular HLA allele that makes them non-responders. So you're getting about 90% protection with the combination vaccine, which is really the great success we're talking about. And that is summarized here. All of what you just talked about is summarized in this nice review that was given by Dr. Beasley. No prophylaxis, 95% transmission, perinatal transmission. When you give the antibody alone, in 1 doses versus 3 doses, there you go, 23%. We saw this earlier. Give the vaccine alone, same principle. Give it together, you've now pretty much taken care of 95% of the population that is going to be carrier-free. And where did you do it? You did it at birth, right off the bat. And then they are free for the rest of their life. And this longitudinal study shows that this program was, over a stepwise period, as these data started getting accumulated, the Taiwanese government instituted these various programs of protection. Initially, it was just when only mothers that were hepatitis positive. Then they gave it to all newborns. Then they gave it to preschoolers. And then they said everybody. And as every 5 years, they picked a bunch of cohorts and found out and determined who has got these, who's positive for hepatitis B surface antigen. And this is the data. And it's a spectacular data because it shows that if you were born before the vaccine protocol is introduced, then you became, as you grew older, you became a carrier. So if you were born afterwards, when the protocol was introduced, then you got protected. So very clearly, this particular story says, give a combination of hepatitis B immunoglobulin and vaccine at an early date, and you're going to protect everybody. And this has now been adopted in the US, and 150 countries have in fact adopted this. It comes with the WHO as well as the American recommendations. The major determinant is, of course, HB surface antigen. More than 1 billion doses have been dispensed with so far, and this is my spectacular success story in medicine. So moving on, let's go on to HIV, human immunodeficiency virus. Now this is the story of, now this, a lot of it started in San Francisco, so we know the story here. Bottom line is, there are today still 35 million people living with the disease worldwide. The vast majority of them are women. And so the mother-to-child transmission is again a big deal when it comes to HIV. So what is the story here? Before we go into that, let's find out some differences between, so this is the situation with regard to perinatal transmission. Of the 15 million women infected worldwide, the vast majority of them are childbearing. And there are about roughly 350 to 400,000 infants infected HIV worldwide. Till date, there are about 2 million infants living with the disease, which is a huge number. Now, in the United States and in developing countries, the rate of mother-to-child HIV transmission is fairly under 2%. It's about 1%. Well, it's about 2%. They want to bring it to 1%. But the problem in the rest of the world is significant. And this, I'll talk about this, is business of pre-antiretroviral therapy versus post-retroviral therapy, which again made a difference with respect to HIV. So before we get into that, let's understand the differences between HBV and HIV. So the title of my talk should actually have been a question mark, actually, because we're really asking a question: can we take that paradigm that we saw in HBV and see if we can translate it into something effective for HIV? The bottom line is probably not quite. And the reason is two different viruses, DNA virus, RNA virus. HBV is a fairly stable virus. HIV mutates like crazy. It's an RNA virus. Reverse transcriptase is a very error-prone enzyme, and that mutation actually helps the virus survive in a very odd way. HBV infects liver cells, and the liver inflammation is what causes the disease. HIV infects the immune system, the CD4 positive cells. Right off the bat, the immune system is gutted, literally, and then tries to make a comeback. When it does try to make a comeback, there's all these mutations that go on. So there's a race between the innate, the immune system of the body, the host, trying to combat the HIV and HIV changing, which is a major problem. So from a vaccine perspective, we have a highly defined efficacious vaccine available and an immunoglobulin available. You don't have those available. That's why I put this in green and red. On the other hand, there are very few effective drugs for treatment of HBV. There's interferon and a few antiviral drugs, but they're not nearly as effective as, let's say, the vaccine and the immunoglobulin. However, today, if 30 years ago HIV was a death sentence on you, today it is actually more like not a fatal disease, but it's a chronic disease. Means people carry the virus throughout. So people have low copies of the virus as long as they're on the therapy. The minute they get off the therapy, man, they're pretty dead. And that is basically, they can get off, the therapy problem would be either because the virus, they become resistant, or these are nasty drugs. So they affect the kidney and the liver. So you have toxicities, you are not tolerant anymore, then you're really in trouble. So the other thing is perinatal transmission, as I pointed out earlier, is a major risk factor in hepatitis B, but it's not such a big risk factor here, but it still is a problem because there are 2 million people out there, the kids out there. So how did they tackle the problem of perinatal transmission in HIV? And this is how they did it. A major trial, this happened in 1994, was reported in 1994. The trial was conducted in 91 to 92, I believe. And the bottom line here is, when mothers were treated with the first drug that was known then, AZT, Zydovitin. And the infants also, so the placebo group was basically mothers treated or not treated before delivery and through labor and delivery. So while they were pregnant, they took 5 pills a day. And while they were delivering, they were given an IV. And when the child was born, it was immediately treated. Under those conditions, big difference between transmission rates with Zydovitin and with placebo. So almost a 70% reduction. Again, there's a 67 to 70% reduction just by treating with a drug. So there's still that gap. So how do you get around that gap? Obviously, we have to look to measures like vaccine and immune therapy, and the story there gets very murky. Because the story of HIV is a story of spectacular struggle, and we still haven't got a vaccine today. And the reason for that is all these biological issues. Huge variability. I mean, if you think influenza shows variations, HIV is about 1,000 times more, literally, if you look at the diversity map. Again, it targets the host immune system, so try to generate an immune response with an impaired immune system, right? Also, once it gets into the host, it again mutates rapidly within the host. So you have what are called founder-transmitted virus, which may be of the R5 subtype, say, and then it continually mutates over years. And by the time year 5 or year 6 happens, it's become an X5 type of virus, much more virulent. And so there's a constant battle between the immune system trying to make antibodies and the virus that's mutating. On top of that, the HIV is very cleverly integrating into the genome, which is why there are what are called latent reservoirs spread throughout the body, in the gut, in various aspects of the immune system. And the HIV just hides in there, so that the minute you stop your therapy, it just comes running out. So that's the issue. And the HIV envelope, which is characterized by a trimeric complex of GP120, which is outside, and the GP41 protein, it's very cleverly shielded. The antibodies, the epitopes that produce what are called neutralizing antibodies are shielded by a lot of glycans. So the envelope structure itself is very cleverly hiding or protecting the virus. And the ones that are the other part of the problem is the part of the HIV envelope protein that is highly immunogenic are available rather to create a lot of antibodies. They're not immunogenic or not really neutralizing. So what it is basically these are the state of the vaccine development today. This is the big one. Probably most people remember that this is a group from Genentech that went and started a company called VaxGen. They made big trial in Thailand. Nothing happened. In fact, in some cases, there were more people got infected more recently. This is the only trial that has shown any success is this, which is like, that's not very good. So what is going on today in research, as far as NIAID and Gates Foundation and everybody else is doing, is they're trying to follow the maturation of the natural antibody from infected people, how it matures as the virus itself mutates. And so there is a process called affinity maturation, so that the antibody produced by what are called so-called elite controllers, who there is a class of people out there who are infected by HIV, people like probably Magic Johnson, everybody knows, who never, they have HIV, but they never get the disease, AIDS. There's something about the immune system, very rare. So they're studying their antibodies, and they find out that over time, their antibodies get higher and higher affinity. And now they try to match with what epitopes the antibodies are reacting against. And on that basis, they're trying to construct various kinds of potential vaccine immunogens. But we don't know where that's going to take us, frankly. That's one. So that's the story as far as a vaccine is concerned. What's the story with antibody? These neutralizing antibodies, this is a structure of the envelope protein spikes. So this is GP120, and this is GP41. This is the CD4 binding site through which the virus enters. Thank you. This is, these are other sites. One of them is a co-receptor binding site on the CD4. This is what is called the membrane proximal external region. And we believe, TheraBiol believes, that this is where really the action is. So these are a bunch of neutralizing antibodies have been produced. There are hundreds of antibodies against HIV. Very few of them are neutralizing. Out of this, maybe about 3 or 4 are neutralizing. And we don't know how long this effect will last, frankly. So what we are approaching today, and TheraBiol, quickly, is to focus on this region here. Because when the virus enters the cell, it starts with binding to this side, and then it flips over. And I don't have, unfortunately, a good cartoon of that. It flips over literally where the 41 has a conformational change that pulls it into the host membrane. So we are focusing on getting those determinants, what we call the conformational antigenic determinants. And so this is our approach. So we take this HIV and we are able to, with a proprietary process, make a non-infective HIV that has lost its DNA, that has lost most of its other internal proteins, the GAG protein and so on, the P24, et cetera, but retains its external envelope in the conformation that it's supposed to be active. And we immunize rabbits with it. And we've actually got a hot bunny that gave us a high titer antibody that was able to show neutralization in vitro. And now the question is, the bunny has, of course, sacrificed itself for the good of humanity. We've taken the spleen cells, and we're going to go fishing for the needle in the haystack using a phage approach. So that's where we are. But this approach can be generalized to other kinds of envelope viruses that have trimeric structures, such as influenza, respiratory syncytial virus, dengue, and Ebola. Okay? And this is the data that shows how the process of making this immunogen is basically non-infective, makes it non-infective. And this is a skid hue model in which you take a skid mouse that is typically used in cancer, but you populate it with the immune thymus cells and liver cells because the HIV needs a human immune system. And so you get this model, and that's the model we're working on. And this is the competition in terms of the major players, and they all have issues. Very few antibodies are really in development. Actually, this is the latest one, and they all have already started showing signs of developing resistance because the top part of the surface of the GP120 that I pointed out is highly mutagenic. In summary, in contrast with HPV, HIV is always, there's a persistent infection, and you have lifelong use of HIV drugs. They're called, antiretroviral therapy drugs. But vaccine and immunoglobulins, we are not there yet. So this is a story of a spectacular struggle. And we hope that TheraBiol will make a difference once we get our antibodies out into the marketplace. And thank you for your attention.